Imagine standing in one of Earth's most unforgiving landscapes. A sea of sand stretching endlessly toward the horizon, where summer temperatures can melt the soles of your shoes, and survival without water is measured in hours, not days. Now imagine being told that directly beneath your feet lies an ocean. Not a small lake or modest reservoir, but a colossal underground water system holding 228 trillion cubic meters of fresh and brackish water, enough to fill 75 lakes the size of Lake Tahoe. This isn't science fiction. This is the Taklimakan Desert in western China, and the story of what lies beneath it is reshaping everything we thought we knew about one of the world's most hostile environments. For decades, China's relationship with its deserts has been transforming before the world's eyes. Where international observers once saw only barren wastelands and encroaching sand dunes threatening agricultural lands, there now stands evidence of humanity's capacity to reimagine even the most inhospitable terrain. Take the Mu-Us Desert, for instance. Over 6 decades, through relentless tree planting campaigns and ecological restoration projects involving millions of workers and volunteers, China successfully reclaimed 42,000 square kilometers of desert land. What was once an advancing tide of sand has been converted into productive grasslands, forests, and farmland. A green barrier that now protects communities and supports ecosystems where nothing grew before. In China's northwestern deserts, you'll also find the world's largest solar photovoltaic power station, generating approximately 4 billion kilowatt-hours of electricity annually. These massive arrays of solar panels transform the desert's greatest liability, its relentless, punishing sunshine, into clean energy that powers cities hundreds of miles away. But the discovery beneath the Taklimakan Desert represents something entirely different. This isn't about conquering nature or transforming landscapes. This is about understanding what has been hidden in plain sight for millennia. A water reserve so vast it challenges our fundamental assumptions about desert geology and raises profound questions about resource management, environmental stewardship, and humanity's future relationship with water scarcity. To understand the significance of this underground ocean, we first need to appreciate the extraordinary environment that conceals it. The Taklimakan Desert sprawls across 337,600 square kilometers in China's Xinjiang region, an area roughly equivalent to the entire nation of New Zealand. Its name, derived from local Uyghur language, is often translated as "you go in, but you don't come out," a sobering reflection of the desert's deadly reputation among ancient traders and modern travelers alike. Positioned in the heart of the Asian continent, the Taklimakan sits thousands of kilometers from any ocean. This geographical isolation is crucial to understanding its climate. Without maritime moisture or moderating sea breezes, the desert experiences some of the most extreme temperature variations on the planet. During summer months, surface temperatures regularly exceed 70 degrees Celsius, hot enough to cause severe burns on exposed skin within seconds. At night, that same sand can cool dramatically, sometimes dropping 40 degrees or more, creating a thermal roller coaster that few organisms can withstand. Precipitation here is almost non-existent. Annual rainfall averages less than 100 millimeters across most of the desert, barely enough to sustain even the hardiest desert vegetation. Meanwhile, potential evaporation rates soar to approximately 2,500 millimeters per year, creating a massive moisture deficit that defines the region's harsh character. Historically, the Taklimakan wasn't always synonymous with desolation. Ancient cities once flourished along its edges, serving as vital waypoints on the Silk Road, that legendary network of trade routes connecting China with Central Asia, the Middle East, and Europe. Caravans carrying silk, spices, precious stones, and ideas moved along these routes, and the oases surrounding the Taklimakan served as crucial rest stops where merchants could resupply before the next dangerous crossing. But as climate patterns shifted and political circumstances changed, Many of these settlements were gradually abandoned, buried by advancing sand dunes, leaving behind only archaeological remnants as testament to the desert's former role as a crossroads of civilizations. Today, the Taklimakan remains one of the world's most formidable deserts, a seemingly lifeless expanse where human activity is limited to its periphery, and where the notion of abundant water seems absurd. Until now. The year was 1984, and China's economic reforms were beginning to accelerate the nation's search for natural resources to fuel its development. A team of 30 geologists received authorization to conduct exploratory surveys in the Taklimakan region, tasked with locating potential oil deposits that could contribute to China's energy security. Armed with seismic equipment, geological survey tools, and enough supplies to sustain them through months in one of Earth's harshest environments, these scientists ventured deep into areas where few had conducted systematic research before. Their persistence paid off. The team successfully identified an oil field along the desert's edge with estimated reserves exceeding 1 billion tons, a significant discovery that promised economic benefits for the region and the nation. But it was their secondary finding that would prove even more remarkable. While analyzing seismic data and geological samples, the researchers detected anomalous readings deep beneath the desert's surface. These signals suggested the presence of something unexpected: vast quantities of underground water. What began as a curiosity soon became the focus of intensive investigation. Over subsequent months, using advanced ground-penetrating radar, seismic surveys, and exploratory drilling, the team worked to map the extent of this subterranean water system. The results were staggering. Their calculations revealed that beneath the Taklimakan Desert lies a massive underground aquifer system containing more than 200 trillion cubic meters of water. Even more remarkably, approximately 20% of this water, roughly 40 trillion cubic meters, consists of fresh water with relatively low salinity, theoretically suitable for human use and agricultural irrigation. To put this in perspective, this single desert aquifer holds more water than 75 times the volume of Lake Tahoe, one of North America's largest and deepest freshwater lakes. It's more water than many countries will use in centuries. It represents a resource that could theoretically transform not just the Taklimakan region, but potentially alter water security calculations across Central Asia. The discovery sent ripples through China's scientific community and raised immediate questions. How did such an enormous water reserve form beneath one of the world's driest deserts? Why hasn't it been completely depleted over millions of years? And most pressingly, can and should humanity attempt to access it? Understanding how hundreds of trillions of cubic meters of water came to be stored beneath an extreme desert requires us to examine the unique geography and hydrology of the Taklimakan's position. The desert doesn't exist in isolation. Instead, it sits cradled within a dramatic basin surrounded by some of Asia's most imposing mountain ranges, a geological configuration that creates what scientists call an endorheic basin, where water flows inward with no outlet to the sea. To the north rises the Tian Shan Mountains, with peaks reaching approximately 7,500 meters above sea level. To the south stands the Kunlun Mountains, even more imposing at roughly 7,700 meters. To the west lies the Pamir Plateau, averaging 4,500 meters in elevation, and serving as the roof of the world, where several major mountain ranges converge. Only to the east does the terrain gradually descend toward the Lop Nur Basin, historically a seasonal salt lake that has expanded and contracted throughout recorded history. These towering mountains are absolutely critical to the Taklimakan's hidden water story. At such extreme elevations, temperatures remain cold enough year-round to sustain massive snowfields and glaciers. These frozen water reserves act as natural storage systems, accumulating moisture that falls as snow during winter months. When spring and summer arrive, rising temperatures trigger seasonal melting. Meltwater cascades down mountainsides in countless streams and rivers, flowing toward the lower elevation desert basin. Many of these waterways are visible on the surface, at least initially. Rivers like the Hotan, Yarkand, and Kiria flow from the mountains toward the desert interior, creating ribbons of life in an otherwise barren landscape. Some support oasis settlements that have existed for millennia. Others peter out as the water is consumed by evaporation and absorption into the thirsty sand. But here's the crucial point. Not all of that water disappears into the atmosphere or is used by surface ecosystems. The transitional zones between the mountains and the deep desert consist of alluvial fans and bajadas, gently sloping plains composed of gravel, pebbles, and coarse sediments deposited by rivers over millions of years. These materials are highly permeable. When water flows across them, a significant portion percolates downward, seeping through countless tiny spaces between rocks and sand grains. This infiltration process has been occurring continuously for thousands, if not millions of years. Each spring, melt season sends another pulse of water underground. Winter snows recharge the system. Gradually, inexorably, water accumulates in the geological layers beneath the desert. Deep underground, at depths ranging from 200 meters to over 1,000 meters, the geological structure changes. Here, sandstone layers with relatively large pore spaces act as natural aquifers, capable of holding water within their matrix. Below these permeable layers often lie less permeable rock formations that prevent water from sinking deeper, effectively creating an underground storage vessel. The dry sand at the surface, ironically, serves a protective function. Unlike surface water exposed to the desert's brutal sun and dry air, water trapped underground is shielded from evaporation. The temperature remains relatively stable, and the water stays preserved, accumulating year after year, century after century, into the massive reserve discovered by those geologists in 1984. This is how deserts can paradoxically harbor enormous water resources, not despite their dry conditions, but partly because of them. The surface aridity prevents water from being quickly recycled back into the atmosphere, while the surrounding mountains provide a continuous, if gradual, replenishment source. When news of the Taklimakan's underground ocean became more widely known, the immediate reaction from many was, "This could solve water scarcity problems across Western China. We could green the desert. We could create new agricultural zones and support millions more people." It's an understandable response. Water scarcity is one of humanity's most pressing challenges, particularly in arid regions of Central Asia, the Middle East, and parts of Africa. The discovery of such an enormous water source naturally triggers thoughts about exploitation and development. But the reality, as scientists and policymakers quickly recognized, is far more complex than simply drilling wells and pumping water to the surface. First, there's the sheer technical challenge. This water isn't sitting in easily accessible underground lakes that can be tapped with simple wells. Instead, it's distributed throughout geological formations at depths that in many areas exceed 300 meters, and in some locations surpass 1,000 meters below the surface. Accessing water at such depths requires industrial-grade drilling equipment capable of boring through solid rock and compacted sediments. Each well represents a significant engineering project, requiring specialized machinery, experienced crews, and substantial energy inputs. In the middle of a remote desert, far from existing infrastructure and power grids, these challenges multiply. The costs are formidable. Deep wells in desert environments can easily run into millions of dollars each, and a single well would provide only a fraction of the water needed for any meaningful agricultural or municipal use. Large-scale extraction would require dozens or hundreds of wells, plus extensive pipeline networks, pumping stations, water treatment facilities, and electrical infrastructure, an investment potentially reaching into the tens of billions of dollars. Even if the technical and financial hurdles could be overcome, there's another significant obstacle: water quality. Underground water doesn't remain pristine during its long residence beneath the desert. As it percolates through various rock layers, it dissolves minerals and accumulates dissolved solids. The chemical composition of Taklimakan's groundwater reflects this process. Analysis has revealed that much of the water contains high concentrations of salts, making it brackish or even saline in many areas. Total dissolved solids, or TDS, levels frequently exceed safe drinking water standards, sometimes dramatically so. High concentrations of fluoride, another common issue in desert aquifers, pose health risks if consumed regularly without treatment. The water hardness, a measure of calcium and magnesium content, is often extremely high, which not only affects taste but can also damage irrigation systems and reduce agricultural productivity if used without treatment. Making this water suitable for human consumption or agricultural use would require desalination and purification processes. While such technology exists and is used globally, particularly in water-scarce nations like Saudi Arabia and Israel, it's energy-intensive and expensive. The costs and complexity increase significantly when these facilities must be built and operated in remote desert locations. Perhaps the most serious concern about exploiting the Taklimakan's groundwater isn't really technical or financial, it's ecological. Groundwater systems, unlike surface reservoirs, operate on geological timescales. The water currently stored beneath the Taklimakan has accumulated over thousands of years. While it does receive ongoing recharge from mountain snowmelt, this recharge rate is gradual, measured in millions of cubic meters per year across the entire basin. If extraction rates exceed recharge rates, the aquifer enters a state of depletion. And this isn't just a theoretical concern, it's exactly what has happened in numerous regions worldwide where groundwater has been overexploited. Consider the Aral Sea Basin in neighboring Kazakhstan and Uzbekistan, where Soviet-era irrigation projects diverted rivers feeding the Aral Sea, transforming what was once the world's fourth largest lake into just a fraction of its former size. The environmental catastrophe that followed, including toxic dust storms, collapsed fisheries, and dramatic local climate changes, serves as a cautionary tale about the long-term consequences of unsustainable water extraction. Or, examine the Ogallala Aquifer beneath the American Great Plains, where decades of irrigation have depleted water levels by more than 30 meters in some areas, threatening the agricultural productivity that feeds millions. In the Taklimakan's case, scientists haven't yet fully mapped the aquifer system's recharge zones, flow patterns, or sustainable yield, the maximum extraction rate that wouldn't lead to long-term depletion. Without this knowledge, any large-scale pumping represents a dangerous gamble with potentially irreversible consequences. There's also the risk of ground subsidence. When water is removed from underground aquifers, the supporting pressure that kept overlying rock and soil layers stable decreases. In areas with unconsolidated sediments, which describes much of the Taklimakan's subsurface, this can trigger collapse of the pore spaces that held water, leading to surface subsidence. Ground subsidence isn't just an inconvenience, it can cause catastrophic damage to any surface infrastructure, create dangerous sinkholes, and permanently destroy the aquifer's water storage capacity. Once the geological structure collapses, it cannot be restored. The damage is permanent. Water systems, both surface and underground, don't really respect arbitrary boundaries. The groundwater beneath the Taklimakan isn't isolated, it's hydrologically connected to water resources across a much broader region. Around the desert's periphery, there are numerous oasis communities that have existed for centuries, depending on shallow wells and springs fed by the same regional groundwater system. These communities, some with populations in the thousands, rely entirely on this water for drinking, cooking, and irrigating the small agricultural plots that sustain them. If large-scale pumping in the desert interior lowers the regional water table, these peripheral communities would be among the first to suffer. Their wells would run dry, their springs would cease flowing, and their way of life, adapted over generations to this delicate balance between available water and human needs, would become untenable. The ecological impacts would extend beyond human communities, too. The sparse vegetation that does survive in and around the Taklimakan, specialized plants like saxaul trees, tamarisk shrubs, and various grasses, depends on groundwater that their roots can access during critical periods. These plants, though not abundant, play vital roles in stabilizing sand dunes, providing habitat for desert-adapted wildlife, and preventing even more aggressive desertification. Lower groundwater levels could kill off this vegetation, leading to accelerated sand movement, more frequent dust storms, and deterioration of already fragile ecosystems. The desert, in effect, could become even more hostile and expand into currently stable areas. Given all these considerations, the technical challenges, the quality issues, the ecological risks, and the potential for irreversible environmental damage, China's scientific community and government authorities have largely reached a consensus. The underground water reserve beneath the Taklimakan Desert should remain largely untouched, at least with current technology and knowledge. This position reflects a notable evolution in thinking about natural resource exploitation. For much of the 20th century, the discovery of such a massive resource would have automatically triggered development projects. The prevailing philosophy was that natural resources exist to be used, and human ingenuity can overcome any obstacle. Today, there's greater recognition that some resources are better left unexploited until we fully understand the systems they're part of and can extract them sustainably. The precautionary principle, the idea that when potential harms are poorly understood, restraint is wiser than aggressive action, has gained ground in environmental policy. This doesn't mean the water will never be used. Rather, it suggests that before any significant extraction occurs, several conditions should be met. First, comprehensive geological and hydrological surveys must map the aquifer system in detail, identifying recharge zones, flow patterns, water quality variations, and connections to other water resources. This research is ongoing, but will likely require many more years to complete. Second, technologies for sustainable extraction and efficient water treatment need further development and cost reduction. Advances in desalination, renewable energy for pumping, and precision irrigation could eventually make limited, sustainable use feasible. Third, alternative solutions to water scarcity in the region should be prioritized. This includes improved water conservation in existing agricultural areas, more efficient urban water systems, expanded use of treated wastewater, and continued development of climate-appropriate crops that require less irrigation. Finally, legal and governance frameworks must be established to prevent unsustainable exploitation if and when extraction becomes technically feasible. These frameworks should include strict pumping limits, continuous monitoring, and enforceable penalties for violations. Lessons learned from groundwater depletion disasters in other regions. The Taklimakan's hidden ocean invites us to reconsider our understanding of deserts more broadly. These aren't just empty wastelands, but complex systems with their own hydrological cycles, ecological functions, and long-term stability. Around the world, major deserts often conceal significant groundwater resources. The Sahara, Earth's largest hot desert, has multiple fossil aquifer systems containing water that accumulated during wetter climatic periods thousands of years ago. The Nubian sandstone aquifer system beneath the Sahara contains an estimated 150,000 cubic kilometers of water, far more than the Taklimakan. Similarly, the Arabian Peninsula's desert regions overlie aquifers that have supported human civilization for millennia. Australia's Great Artesian Basin, beneath the arid interior of that continent, holds roughly 65,000 cubic kilometers of water. These discoveries tell us that water on Earth is distributed in ways we're still learning to understand. The hydrological cycle isn't just about rain, rivers, and lakes visible on the surface. It includes vast underground components that operate on different timescales and follow different rules. They also remind us that what appears scarce at the surface may be abundant below. But accessibility doesn't automatically mean resources should be exploited. True resource wisdom lies not in extracting everything we can, but in understanding complex systems well enough to use them sustainably, or to recognize when they're better left undisturbed. The story of the Taklimakan Desert's underground ocean is ultimately a story about choices. Choices that will determine whether future generations inherit a world where we've learned to live within natural limits, or one where short-term thinking has depleted resources that accumulated over millennia. Standing in that desert today, with 228 trillion cubic meters of water beneath your feet, it would be easy to see a solution to water scarcity, an opportunity for development, a resource waiting to be harnessed. And those perspectives aren't entirely wrong. This water does represent potential value. But perhaps the greater value lies in what restraint teaches us about our relationship with the natural world, in recognizing that not everything we can take should be taken, in understanding that true wealth sometimes means preserving options rather than exercising them immediately. The water will remain there, held in ancient geological formations, slowly flowing through rock and sand as it has for thousands of years. And perhaps that's exactly where it should stay, not because we lack the technology to extract it, but because we've finally gained the wisdom to question whether we should.